So, hello there, that's Lab02 report for Physics 112 class in Georgia Tech. And let's begin. So, the introduction, the purpose of this lab was to observe the projectile movement in real life and compare it to modeled one with the same starting conditions. And deduce the drag coefficient this way, as well as deduce if we can find terminal velocity this way. Uh, Models used to utilize the second Newton's law, F net equals ma, the law of gravity, F graph equals mg, and the drag force, F drag equals minus b, that's the coefficient we're looking for, v squared. Preview of the results, the drag coefficient was found to be 0.1. So, here's the video on the experiment. Yeah, the object chosen was a tape roll of 11 centimeters diameter. The initial height was about 1 meter with x being 0 because origin was set to be below the start point, the point where I released the tape roll. The assumptions are that the friction against the air is negligible, as well as the heat produced in it, so all of the energy goes into the motion and drag force through. So the roll was thrown until it landed. Here's the video again. Yeah. So what did I do is to upload the video in Tracker. I tracked the movement of the tape roll until it landed. Here is a screenshot of how I did that. The results I got are here, and then I coded a model for this movement. Here's the code. Here's the F drag force calculation, F net force calculation. Yeah. So here's the two models. The left one is, the left one is no drag force, B equals 0. As you can see, there is no orange arrow, that is for drag force. And the right one is with drag force, or drag coefficient equals 0.1. I get this coefficient by trying different coefficients until I get the similar results to the experimental ones. Here you can see the orange arrow, the drag force, purple one, the velocity, and cyan one is the F of F net, not F net, gravitational force. So, here's the results. At the left, you can see the axis, x values, and y values for the experiment, for no drag, and drag b equals 0.1. And the time it took about 0.5 seconds for the object to land. At the right, you can see the graph. The blue one here is the experiment. The orange one is no drag model. As you can see, it would land further than needed. So I was adjusting the drag B till I got the modeled graph and experimental graph aligned. And I got this way the green line, the drag B equals 0.1. And as you can see, the blue one and green one lines don't align at the top. That's because of an error resulting in bad angle, coming from bad angle recording, making the upper height values too high than they actually are. You can see it here in Tracker because the angle was looking on top slightly. The y values could be recorded as higher than they actually are. So, what if the object was run straight up, the trajectory graph would be a mess, just a mix of straight lines. It would be just, all lines would be straight here. So it would take longer to land if speed was the same, because it would all be in y direction instead of partially in x direction. Thus the time to land would be longer, because we released it with the same speed, just up. So it takes longer time to fall. What does it mean, terminal velocity? At the left you can see the velocity against time, and at the right too, velocity against time graphs, but at the left it's b equals 0.1, at the right it's b equals 0. And you can see that at the left, the x against time is curving, and it starts curving about at s equals 0.3 centimeters, or is either 0.2 or 0.3. So we can say that the terminal velocity is about minus 2 meters per second there when the drag force actually starts working. So the conclusion is that we successfully can use models, the globe script, to simulate real-life projectile movement, introduce drag forces, and terminal velocity from that. So yeah, that's it. Thank you for your attention.